Hello. Good morning. Can you guys hear me now? Okay, let's try this.
I can hear you.
I think. I dropped my mic and I guess it doesn't work. Can you guys hear me?
Yes.
Okay, is it clear or it's kind of soft or what?
No, it's pretty good.
Okay, so I think I broke my mic. I'm kind of bummed because that was a good mic. Anyways, good morning, everybody. How are you? Welcome back. So you hear me better than last time. Oh, well, that's good. So maybe this is a better mic then.
I think it is, yeah.
I've been using the wrong mic. Okay, well, I'm happy to hear that. So good morning and welcome back. We have a lot of fun things to do. I do want to ask right now, let's see, let me just check to see who's on YouTube. Some people are on YouTube. Nope, nobody's on YouTube. So we're all on Zoom right now. I think some people will probably join us on YouTube. Let's see, I know what I want to do. I want to go ahead and change it to speaker view, and I have to pin myself so so that it doesn't change back and forth. So if you go onto YouTube, you'll see the same thing. All right, so I do want to mention that you guys had homework problems to do that were due today, and a lot of people submitted them, but a number of people did not. And so I want to start off, first of all, does anybody have any issues with the homework? Were you able to solve the problems? Maybe you just didn't upload them yet. Anybody?
No. I had an okay time.
Yeah, you did find the last problem though. You got it a little reversed, but other than that, it was fine actually.
From the Earth's perspective, 100 years passed, and I kind of just put it in days, and to me, it's the same answer. 3.65 days pass for every day that passes in space from.
Oh, okay. Maybe I misunderstood that. Okay, I got you. I just didn't read carefully enough. Okay, sorry about that. Yeah, you're right. Okay, but so they experience 100 times as much time. Okay, great. So the question asked if the rocket people experience a year, then how many years are passing on Earth? And so I guess I was looking for 100 and I didn't see 100, but you're right, that's true, never mind. Okay, sorry, forget that then. I mean, I gave you full credit anyways, it's not an issue.
No, right, I know,
yeah.
It's not a big deal, I just.
Yeah, I guess I was trying to think about like what it would mean if we really go on an interstellar voyage at relativistic speeds. What does it mean? Can you come back and, you know, say hi to your family again?
Well, I watched a video by 3 Blue 1 Brown about time dilation and length contraction. And that was that little drawing that I included. Apparently, during the time where you change velocity, there's unaccounted for time when it comes to going out and coming back to zero, or wherever your reference point is. So according to zero, the same amount of time passes from 1 to 10, but an unaccounted for period of time passes because of the change in velocity.
Right.
The amount of time that you take changing is relative to the amount of time that it takes for you to change direction and come back at the same velocity. So
then who's older? You're saying that if you get off the rocket,
the older person is the one who experiences all the time, and the younger person experiences the unaccounted for time, according to the Earth observer.
Okay. Well, so the Earth observer is one of the people though.
Right, but the unaccounted for time person, the person on the spacecraft, only experiences like 2/3 of the time.
Tom asked the question, how big would a circle have to be if you're moving at 99.9% the speed of light So the centripetal acceleration does not kill you. That's a very interesting question. So we can come back to that, Tom. That's fun. Very provocative. A pretty big circle. Yeah. So actually, so I was going to talk about general relativity today. So maybe if we can just kind of leave that out for a second. We're trying to keep. Yeah, it's a good point actually, Christian. So that in the accelerating frame of reference, special relativity technically doesn't apply, right? It doesn't really apply. So when you're accelerating or you're in extreme gravitational fields, you can't really say that you're in an inertial reference frame. It's really not the same. It's not true. And so the underlying assumptions for special relativity are that you are in an inertial reference frame. You're moving at a constant velocity relative to someone else.
Is there something out there that has us say that it's true for all cases?
Is there something that's true for all cases? No.
Right. You
said
it's
true
not,
for all cases.
It's not true for, well, last week we talked about laws of physics are the same for all inertial observers at constant velocity, and the speed of light is the same for all inertial observers. But is there something that allows us to assume that there's one rule for everything?
And what do you mean by one rule? Like one law of physics?
Well, I mean, we can consider light pretty constant from our perspective, right?
Yeah.
It travels at a speed of light for everyone.
Okay.
So, I mean, I guess what I'm getting at is that is special relativity flawed in that sense? Like, why can't it be applied to everything?
Well, I'm not sure why you would consider it flawed. It just says that
I just wanted to ask about like why it's true for some cases and not others, and is there something that fills in that blank?
Well, actually, it's just actually if you think about it, let me come back to yeah, that's a great question actually. Thank you. When we talked about making artificial gravity with an orbiting space station, did that make sense to you? The way that you rotate the space station, the floor has to push on you to keep you moving in a circular path, right? So the floor exerts a force on you that you feel kind of like gravity. It's an artificial gravity, right? That makes sense?
Yes.
Okay, so you have to understand then that is an interesting situation, right? If you didn't know you were on an orbiting space station, Christian, right? If you didn't know that, then how would you know what was really going on, right? You would say, oh, I'm in a gravitational field.
Right.
How do you know what's real and what's just a manifestation of the acceleration of your reference frame?
Right. That's a lot of the premise for the movies. You know, they're like, oh, where am I? And they find out they're on a space station because there's no difference in gravity or whatever.
Sure. Because they're really, so we'll talk about that a little bit later, but when you talk about the laws of physics being the same, right? One of the problems is that when you accelerate a reference frame, you get a fictitious force. You get a force that you can't explain. You have no understanding of where it comes from. It's just there. You can't explain it. It's kind of like, do you remember when I took that tray, the Greek waiter's tray, and put the cup of water on it and swirled it around? Did I do that with you guys? I feel like I did. The artificial gravity idea. The cup just has no knowledge of what's going on. Why is it that the water level stays the same? It doesn't. Yeah, okay, you were in the front. Okay. The water in the cup just, it doesn't move, right? It has no understanding of what up and down are. It's just, it has no understanding that I am exerting an outside force on it and causing it to accelerate. It just does what it's doing. It just feels gravity, and it happens to feel a little more sometimes or a little less other times. And the water level is always finding its equanimity, right? It finds that equal level everywhere in the cup in response to the gravity that it feels, but it's not the same gravity that you and I were feeling. And the reason is because there was an outside force. How about this one? You fired a gun, you've shot a gun before?
Yes.
Okay, so if you fire a rifle, you might know that the scope is calibrated for distance. And the reason is for something you know about, right? It's called the Coriolis effect. Have you heard about that?
Right.
Okay, so what does it mean, right? We are actually living on a rotating Earth, and that rotating Earth has a tiny little effect, but it's noticeable. It's not something that you can ignore anymore, especially the bigger the distance. And so we call it the Coriolis effect, and we understand what it comes from. But if you're the bullet, you have no understanding of why you're flying the way you're doing. In fact, you're flying as straight as you can fly, right? You're just, you feel your forces and you're responding. You have no understanding of where they come from. So if the problem is, if you're in an accelerated reference frame, there's extra forces that you cannot explain. They have no source that you can identify, right? They just exist. So when I say to you, there's a force of gravity and it's dependent on mass, you can kind of, understand that the source of the force is this disturbance that's due to the mass. Now, of course, Einstein gave us a revelation, and he said that in fact, you don't understand gravity at all, because what you interpret as a force is a manifestation of the curvature of space-time. We are in a curved space-time that gives us a feeling of a force. But the laws of physics kind of rely on this uniformity. And if you have an accelerating reference frame, there is a force that's causing that you cannot explain. You have no knowledge of it. And so it wouldn't be possible to establish a uniform set of laws anymore, because each one would be dependent on what your particular acceleration would be. Does that make sense?
Yes.
Okay, so that's why we don't want to go crazy with that one, because it's really a path that you will never escape from. There's no absolute frame of reference. It does not exist. So it's one part of what I want to talk about today. So where was a request to go over the last problem?
How can we talk about the Big Bang in that sense then?
Pardon me, one more time. Sorry, I didn't quite hear you.
It's all right. I mean, if you're saying that there's no fixed reference point, then how can we talk about the Big Bang?
Well, okay. That's a great question. Can we table that for just a moment though, or not for a moment, for a little while? Yeah. It's a good point. But I want you to understand there is a self-consistent way to describe the Big Bang, and it will not violate any of the things that I'm telling you. And the problem is that much of the universe does not exist in an inertial reference frame. A lot of the universe is not an inertial reference frame relative to us. And so we cannot use special relativity for every possible situation. There are many situations where it does not apply. So you just want to be aware of that. So actually, I don't want to get into this too much quite now, but one of the things that we'll discover is that things that are kind of close to us are more likely to be inertial reference frames, much more likely. When they get further away from us, unfortunately, the further away they go, the more likely they are going to be accelerating relative to us. So one of the things that you want to get is that it's pretty big, right? I mean, in terms of human space, the sizes I'm talking about are huge. They're humongous. It could be almost the size of our universe. Not our universe, our galaxy, sorry. And that's, on a human scale, that's just almost infinity as far as we're concerned, right? I mean, not in terms of what we can see, but in terms of where we can go, right? Right now, we are not capable of getting very far. So in human scales, relativity is going to be really interesting and applicable to real problems that we have to deal with, right? Which are shorter scale distances between us, where there is a relative velocity which is constant, right? A constant relative velocity. So it does apply to enough problems that it's worthy of our discussion. But we'll also discover, that it does have a regime, right? It doesn't apply to every situation. So let me just talk about this fourth problem. We had a request to talk about that. And it was supposed to be kind of simple, actually, but let me just look at the question. I'm gonna see here. Actually, I could just, what am I talking about? Dang, I need to use my skills here. I could just go right over to the question. Okay, here we go. Here's our question. Skills, okay. So the fourth question, the twin paradox. And again, the paradox is only there when you don't know about what Christian was alluding to earlier, the idea that the acceleration is going to solve the problem. But the twin paradox describes a pair of twins, one who is on Earth and the other one travels away from the Earth at a large velocity. So I gave you the gamma, which is kind of the most important factor, right? The twin on the rocket ages by 1 year. How much does the twin on Earth age? The paradox is that if you are in the rocket, the Earth is the body that is moving. How does this make time on the Earth look? So, this is a paradox, right? Who's moving? And the answer is, if you just have two frames of reference relative to each other, and this is the typical notation. This is if you go to school in physics and get a degree in physics. This is the diagram that you're going to see. We're going to have the fixed reference frame and the moving reference frame, okay? And actually, we're going to use this diagram a couple of times today to talk about some ideas. But the idea is that from the point of view of the fixed reference frame, I can see this moving reference frame moving with a velocity v, okay? And so I'm going to use v as the velocity of the reference frame. And in this point of view, what happens? Well, if I am in the frame of reference that is moving and I measure the time to be 1 year, right? And you use the frame of reference of the experiment, which is the person doing the measurement, to be the frame of reference. Then according to the person who's watching from the stationary reference frame, from the fixed stationary, we call it, sorry, then it's gamma times the time, right? So when I gave you the gamma of 100, we kind of solved the problem. It's really easy. It's 100 times 1 year, right? So that's the answer. It's 100 years. Okay, unfortunately, we could switch perspectives. Okay, and we could let the rocket be the fixed frame of reference. And then what do we see happening, right? What do we see happening? This is the paradox, right? We see the Earth moving this direction with the same velocity that we had up here in this problem, which means that from this point of view, I also see a gamma of 100 for the Earth. And so when I see 1 year passing, I would interpret this as, I would say, the time for me is now this time, right? It's 1 year. Then I would say that the Earth person is experiencing T0, which would be T divided by gamma. Okay, I would say they experience, as Christian said, 3.65 days. Okay, so that's the paradox, right? Which one is moving? And the answer is, if you just have two reference frames moving relative to each other, there is no way to distinguish who is moving from who is stationary. There does not exist. So get rid of any preconceptions that you have. And do not say it has to be the Earth, okay? Because if you have this situation, you actually have no knowledge that that is the case. If you just jump into this picture, you don't know. But that is not how it really happens, right? So the reality is that we have other knowledge, right? And so what I said to you is that originally the rocket and the Earth were in the same frame of reference. They were together, right? They were together on the Earth. And so because of that, we have previous knowledge. We know that when we get to a new situation, right, and we say, well, somebody's moving, the answer is who's moving? Well, the one that accelerated, which means that it must be the rocket frame of reference that is the moving reference frame, and the Earth becomes stationary. But it's only with this previous knowledge that you can do this. Okay, so there's an acceleration phase required, and because of that, we know for a fact. So one of the things that you want to be aware of is that even though there is a contribution for general relativity, we'll talk about that a little bit later, there is still a real effect. It really is true that if we watch from Earth, this person ages at a slower rate than we do, right? Or this particle ages at a slower rate than we do, okay? So actually that problem with the muon, I think we had, again, a couple of little issues with the solution. It was supposed to show you that if you use the lifetime of the muon as a proper time, this is problem number what? 2, 3, I forgot. 2, problem number 2. 2.2 microseconds, which is 2.2 times 10 to the minus 6 seconds, and it's traveling at 0.9997 C, right? So 2.2 is problem number 2. 2.2 microseconds. That's 2.2 times 10 to the minus 6 seconds, right? Micro is 10 to the minus 6. And if you're moving at 0.999, how many nines again? I forgot. 0.999, 3 nines and a 7. Okay, see, I got dark here. Sorry, my lights turn out. Okay, so your speed of the reference frame is 0.9997 C. Okay, then you could say, well, you know, with no time dilation, right? If there's no time dilation effect, then how far would the muon travel? So distance is just velocity times time, like this, right? So no time dilation. And we find out that it's not very far, right? So you're going to use 0.9997 times 3 times 10 to the 8 times 2.2 times 10 to the minus 6. Okay, so I've got some numbers. Now maybe I should have used a better number for C, except I only have 2 significant figures here. So even if I use 2.998, right, it's going to end up giving me less significant figures. But why don't I put 3.00, right? That's 3.00, 3 significant figures. Okay, so we got an answer. Actually, I think people got this. I mean, a lot of people got this one. So what was the answer? Did anybody remember? You got it in your homework? You did your homework?
I got the lifetime distance with time dilation at
without time dilation, sorry.
As 659.4 meters.
Okay, so we're going to go ahead and call 659.4 meters. If I round it off to 2 significant figures, it's 660 meters. Okay, so all right, so that's not very far, right? It didn't get very far. If time dilation is a factor, what's the gamma for this, right? This is a pretty significant gamma. Who got the gamma for 0.9997? I can go look at your answers. If you guys are here, I would appreciate somebody just telling me. Anybody? Christian again? What'd you get?
I'm trying not to.
Oh, here we got 40.8. Thank you. Okay, 40.84. Okay. And so if we have 40.84, you see what's going to happen is we're going to get 40.84 times the distance because we have 40.84 times the time. So the true with time dilation, you get a distance which is 40.84 times as much, which is, what do we get, 26.8, about 27 kilometers. Well, now we can make it, right? We can make it, actually, that's still not very far. How big is the atmosphere? Anybody look it up? 10 kilometers? 10 kilometers, really? You think so? Okay. I would actually say 100 kilometers if I were going to say anything, but maybe these particles are probably created a little bit lower. But anyways, it turns out that even this lifetime is not quite something that's absolute. So yeah, you can't breathe. Okay, that's a good point. So
out to
if
12 miles, 6 to 20 kilometers.
6 to 20 kilometers. Okay. All right. So anyways, these muons, by the way, they do make it to the surface. And one of the things that's kind of interesting is there's a really neat thing that I can tell you about. Actually, I just find it so fascinating, is a field of archaeology right now uses muons. I don't know if you've heard about this.
For aging.
To find hidden rooms inside of the pyramids, right? So it turns out they are, it's called, here it is. Actually, I should just go to Wikipedia because, of course. And here's a Nature article. I just find this so, Nature's pretty awesome, by the way. So I'm gonna go to Nature. I like Nature. Cosmic ray particles reveal secret chamber, right? This is so cool. They put this cosmic ray detector down at the bottom of the pyramid, and when they do, they find out that they can see that you get more muons or not. If there's a solid material, you're less likely to get the muon, and if there's a vacancy, a space there, you're more likely to get the muon. So just from the difference in muon detection, they were able to see the possibility of this hidden chamber. I don't think it turned out to be too much, but I just think it's such a cool idea, So muon tomography is the technical term now. If anybody says to you, yes, I think muon tomography is the answer, you can answer the question, you understand what they're talking about now. So using cosmic rays to generate a three-dimensional image of volumes. Wow. Oh my gosh, this is actually something I want to talk about. Okay. No, that's not it. That's not Compton. I want to talk about Compton scattering today. Okay, so anyways, muon tomography. Okay, so anyways, we talked last time about, yes, okay, so Tom put a good point here. He put half-life, and actually that's kind of what this is. A muon decay doesn't happen in an absolute amount of time. A lifetime is the average, the time required for half of the muons to undergo decay. And so it turns out some of the muons will live longer than others. So it's not actually that all the muons live the same amount of time. It's a statistical thing or a probabilistic idea. And so they don't all live the same amount of time at all, actually. Okay, so I do want to talk to you about an idea, a pretty important idea in relativity, and that is what Einstein was doing when he came up with the laws of special relativity, was trying to improve what was currently understood. So you want to know that Newtonian physics is pretty dang cool, right? It's not bad. It's really useful, and we continue to use it. It works pretty well. I mean, it does have issues when you have friction. You've got to really massively correct for that. But in space, there's very little friction, right? So it works incredibly well for orbital dynamics, and you can actually do a lot of really great situations. But I want to talk about one of the ideas that Einstein had early on, and it motivated him to change his laws, and he added in this extra term, and I don't think I've talked about it before. Did I talk about it already? Anybody know what I'm talking about? Some of you may know, but if you know about it from another source, then I need to talk about it today. So I want to tell you that that there's classical physics, and there's relativistic, right? Classical and relativistic, right? And one of the beautiful ideas is that if something worked pretty well in classical physics, you don't really just want to throw it away, right? It's not that it's a bad idea. It's actually a really useful idea. For example, the concept of momentum, right? Conservation of momentum is a pretty big deal. And classically, the momentum is mass times velocity, right? Well, what is the equivalent in relativistic terms, right? Now we do have an issue. I've got the letter V here. V it represents velocity. And we're going to have a little problem today because there's more than one V, right? What is this velocity? The velocity of a particle. But now we're going to try to talk about it from the frame of reference of a moving observer, or from, you know, or vice versa, right? If from a fixed observer's point of view, from a stationary observer's point of view, what does it look like? And so I need to actually use another symbol. Okay, so in a moving reference frame, okay, in a moving reference frame, I'm going to let the reference frame have a velocity v, right? This is the moving reference frame. But if I have a velocity within that moving reference frame, what am I going to call it? Okay, hold on. I want to be consistent with what I'm about to do. So give me 1 second. Okay, let's see. All right, so I'm cheating. Sorry about that. Okay, I did want to use that. Great. I wish they would just draw a picture. That's what I want to do. No pictures. Okay, well, it doesn't matter. It's fine. I got it. And actually, I cannot derive one thing I'm going to do with you without calculus. So unfortunately, I'm going to have to, some of you can derive it, but the rest of you will just kind of accept that this is the formula. Okay, so back to my story. Okay. So if there's a velocity within this moving reference frame, I'm going to call that u, and I'll put a prime here to represent it's the velocity as seen by the moving reference frame. If I have a stationary reference frame, right, that's S, then what do they see, right? And the answer is we're going to call that u, right? So from the point of view of the observer over here, the velocity of that thing is going to be called u, right? I know it's the same thing. Whatever. Okay, we'll come back to that. I actually want to talk about that. Anyways, so what am I going to say? If I have a moving reference frame and if I have a moving reference frame, what do I want to say? Now I'm a little confused. Hold on. Anybody know what this is? Okay. It's actually really confusing. I wanted to just write something down, and now I just realized I'm a little confused. Let me just write it down. What is it? Okay. I want to write down the relativistic momentum. Okay. And the answer is, okay, all right, that's what they put. Okay, that's weird though. What do you do in the lab frame? Uh-oh. Gotta go back. Maybe I'll just show you guys what I'm doing. I'm looking at Wikipedia. I'm looking at relativistic. So I wanted to write down gamma mv, but I actually, okay, so actually this is a little confusing. Yeah, okay. All right, so I just realized what I'm going to do. I'm going to try to keep it simple. Let's pretend for a moment that it's not moving at all. Let's make it easy, right? Then what is it going to be? The relativistic momentum is going to be gamma times m times v, okay? Because it's not moving in this frame of reference, but we see it, the whole frame of reference moving. This is the new formula. Okay, so this is kind of beautiful, right? All you do is change from mv to gamma mv. Okay. And actually, okay, let me get back to that. Okay, actually, no, let's do it now, right now. Why is it that gamma mv is the right expression? Well, let's talk about that, right? So P equals gamma mv. What's that? M times v times 1 over the square root of 1 minus v squared over c squared. Okay. So what do we want to happen? Well, what if you're not moving near the speed of light, right? This is for relativistic speeds, which we didn't really define carefully, but it's anything that's moving with a significant fraction of the speed of light. What happens if you're not moving near the speed of light, right? What if your speed is really, really slow? This is less than c, right? Very small compared to c. Then what should happen? Well, what happens to gamma is it becomes close to 1. And therefore, P becomes, right? Well, you could, exactly. I mean, if you put in 0, definitely. But the idea is that this relativistic momentum, which is gamma mv, just becomes mv, which is the momentum that we know already, right? We recognize that. That's the right equation. That's the right equation. Now, I do want to show you a trick, not a trick, but an important idea. And last time I actually had problems with it, but I think this time I understand where the problems are. Let me rewrite this gamma factor, which is 1 over the square root of 1 minus v squared over c squared. Let me rewrite it as a parentheses. Yes, that's right. In the limit that v becomes 0, that is in fact what happens, okay? But I want to show you an expansion concept, right? I can write this as 1 minus v squared divided by c squared to the negative 1/2 power. Okay. Now, if you remember last time, I showed you a very interesting thing, right? That if you have 1 plus a small quantity, epsilon, raised to the nth power, whatever n is, that to the 0th approximation is 1. Okay, that's called the 0th approximation, right? Just ignore it. To the first approximation, it's n epsilon, 1 plus n times epsilon. That's the first approximation. To the second approximation, it's n times n minus 1 epsilon squared over 2 factorial. Okay, so you might recognize some of these things from last time when we were doing the series expansion, and then you can keep going. But if epsilon is a really, really small number, I can pretty much ignore this quantity, right? And so I want to try to do that with you and just pretend, actually, I'm going to ask the question reverse. What does it mean, right? If I ignore this term, how big does it have to be? And we'll come back to that in just a moment, okay? But I want to give you this as your first approximation then. What is this equal to? And the answer is 1 plus, right, n, which is negative 1/2, times epsilon, which is negative v squared over c squared. Okay, so to first approximation, I get 1 plus v squared over 2c squared. That's the first approximation. Okay, you notice it is plus, right? Gamma is greater than 1. Okay, so why did I want to do that? Well, because I want to tell you about Einstein and a problem that he had with kinetic energy, right? Take a look. Actually, it's not a problem with kinetic energy. It's not a problem at all. In fact, I can easily write down the kinetic energy formula. Classically, it's 1/2 mv squared, right? But the relativistic kinetic energy is something a little bit different. It's gamma minus 1 mc squared. Okay, I'm going to be very precise. Actually, let me put in the m0 right here. So what does the m0 mean again? The rest mass. Yeah, rest mass. So measuring it in the frame of reference where the material is at rest. So when you look at this formula, what do you think? Is it beautiful? And to Einstein, even though it's right, he thought it was pretty ugly. Okay, so first of all, exactly, ugly. It is kind of ugly. I mean, look at this ugly. This is ugly. This is beautiful. This is ugly, right? But I do want to prove to you that this is correct, right? So it's correct because in the limit of small velocity, right? In the limit, not the limit, in the case where v is much less than c, small velocity, the relativistic formula has to become the classical formula. So the kinetic energy, gamma minus 1 mc squared, right? What does it become, right? So remember that we just said that gamma is approximately 1 plus v squared over 2c squared, right? So when you substitute this in, gamma minus 1 mc squared, right? What do you get? You get v squared over 2c squared, right? That's gamma minus 1 times mc squared. Well, the c squareds cancel and you get 1/2 mv squared. This is correct, right? This is right. Exactly. So it is ugly. So, but do you see it's correct, right? It gives you the correct kinetic energy formula when v is small. If it didn't, we would have screwed up. We would have the wrong formula. It's consistent, right? It's consistent with the normal classical problems that we have, experience with. But he said it's ugly. It is ugly. Okay. And so he decided, it's a whim. It's absolutely not for any reason that he could explain at first. He said, let me introduce a new concept, the relativistic energy. A new concept, right? And let's call it gamma mc squared, okay? So that's beautiful. That's beautiful. But how did it occur, right? What is going on? Why is the v still squared? Because if you go back to our epsilon term, the epsilon, or the small quantity, is v squared divided by c squared. So that negative v squared over c squared is the whole epsilon term. So it includes v squared over c squared. So you're confused by why, yeah, I took a square root. But the idea is that it doesn't matter that it's a square root. It's just something. This is a really powerful thing, by the way. And if you don't believe that it's right, what you can try to do is put in numbers and see if your calculator actually gives you the same result. And so maybe that's what we should be doing, right? We should try to figure out what situation is this true, right? What values of velocity would allow this to be true? And they're going to be small, right? So let's come back to that. But do you see, so just what happens is that the power comes down in front of the epsilon. And I know it's weird, but we just ignore, it's not, don't worry about the square root. That's the power right here. That's the power. So it comes here like this, okay? And But the question is, does it actually work? Well, it does, it works, and this is consistent. This gives us the right kinetic energy formula. If it didn't give us the formula, we would have made a mistake. But it is ugly, and so he threw in something more, right? How do you get this energy? And you want to know that this is, in fact, the kinetic energy plus what? Well, exactly enough to get rid of that factor of 1, right? So plus mc squared. That's what it is. Okay. So this is what he decided, right? He's like, let me throw this in, added this term. And now it's beautiful, right? You just add this term. What is that? Well, what is that? This is an interesting situation. It says if V is 0, your kinetic energy is 0, but your energy is not 0. You might call it your rest energy, right? And it's E equals mc squared. And you might think, oh, that's the famous Einstein equation, but it's not quite. It's actually not quite the famous equation. This is called the rest energy. And it says that something that is at rest still has an energy. Now, Einstein wasn't stupid, okay? I mean, he had this insight. He didn't know why he just knew that this is a more beautiful expression that is then more consistent with the other equations. So if I go back to my picture here, right, I don't actually have well, I guess I do. I have this new concept called energy, the total energy, and it's mc squared. And it says that if you're at rest, you still have this energy, and your total energy when you're moving is mc squared. So that's not what I wrote before, right? He actually did not understand the idea. He finally understood it, but that mass is also relative to motion. That if you go back to the equation, E equals gamma m0 c squared, these two equations are identical. If m equals gamma m0. This is called relativistic mass. So Einstein did not understand at the time, but this is the famous equation right here. This is the famous equation, E equals mc squared. This is the version of it when they're not moving, which is also, it seems the same, but it's not exactly the same. It says that things that are not moving have a certain amount of energy called the rest energy. And what is it based on? Well, he again, wasn't stupid. He said maybe the energy required to assemble the matter, right? Everything, right? From the constituent parts, right? The protons, the neutrons, the electrons, putting it all together takes energy. Let me call that the rest energy, right? Let me call that the rest energy. But really, it's probably something even more fundamental than that, right? Matter itself is a form of energy, right? Matter, this is kind of a big deal, right? E equals mc squared means that matter is a form of energy. Well, that's pretty exciting. And you guys may already know that that's how nuclear fusion works, right? That inside the sun, little tiny bits of matter are being destroyed, but not exactly destroyed. They're being converted into other forms of energy. This is beautiful, right? And so actually this concept of conservation of energy is getting even better. If you go and you look at CERN, right, the Large Hadron Collider, and actually I want to talk about that too, but getting off on a tangent. They smash particles together at nearly the speed of light. Why? Well, because that means they have a lot of energy, right? These very high energy particles collide, And where they collide, all of that kinetic energy, and actually just energy, all of that energy is concentrated into a very small volume. And what they see happening is kind of amazing if you didn't know this. They see particles spontaneously created out of this situation, right? Particles that weren't there suddenly appear out of this, right? And the reason is E equals mc squared, right? The energy that was originally kinetic energy can be converted into matter energy in the Large Hadron Collider, LHC, CERN. That's actually an acronym, so I should capitalize it. Okay, so anyways, anybody have questions? Anybody? So I want to make you happy and tell you that conservation of energy just got better. If you now include matter energy, this equation is even better than before, because you can now describe some really incredibly energetic events and where the kinetic energy seems to be destroyed. So if you take two particles moving at the same speed and you smash them into each other, in classical physics, you would say that the total momentum is 0 in this frame of reference where I see this happening, which means that afterwards there's total momentum has to be 0, conservation of momentum. And conservation of energy says that the energy that they have before the collision has to still be there after the collision. But the particles actually pretty much destroy each other in the process of colliding. And out comes all of these other, much more mass comes out than what went in, right? The mass that went in was pretty small compared to the mass that came out. Okay. So we like conservation of energy, right? We love it. We love it. And now I want to take it all away from you. Isn't that nice of me? I want to take it all away. Because it turns out that even if we like conservation of energy, we have to understand something pretty important. How much energy is there? How much energy is there? So imagine I am watching, you know, a particle with a mass m0, right? Well, when I measure it at least, right? Oh, wait a second, we want it to be moving. So we're going to put it in a frame of reference that is moving relative to us with a speed v. Which means I will see that it has an energy of mc squared, right? Where m is gamma times m0. Same thing. So in fact, I don't see this mass, right? Maybe I know that originally it has a mass m0, but in fact, what I see is now that it has this much mass, right? It has more mass than it did before because of this motion. And okay, so that's what I see. But now, what if you are in the particle's frame of reference? Okay, how much energy does the particle have? Well, the particle's not moving, right? It's u, I should call it u. U is 0, u, right? U is 0. U is the speed measured in the frame of reference, right? Where you're not moving. Okay. That's confusing. I'm going to come back to that. All right. So in the particle's frame of reference, it has no, well, it still has this energy. It has E0. So do we agree on the amount of energy? And the answer is no, right? Energy is relative. Motion is relative, time is relative, space is relative, and now we find out energy and mass are relative to each other. So you can't actually say conservation of energy for the universe right? You have to say, from where are you watching? It's always going to be relative to your frame of reference. Where are you watching from? There is no absolute amount of energy for the universe. It doesn't exist, right? There's just energy and your perspective. So as long as you're consistent, conservation of energy works. But as soon as you change frames of reference, that amount of energy will change, which is a little bit disappointing, but that's life. Don't worry about it. Just let it go. Everything is relative. Okay, so I actually wanted to, actually, let's come back to that problem. Let's do something where you guys give me a little feedback here. I told you that we're going to go ahead and do this approximation. Gamma is approximately 1 plus v squared over 2c squared. Can we find out what value of v this works for? What value of v does this work for? Okay, so I want to help you see what that might be. You don't actually need to worry about the v. Let's just worry about the epsilon, right? So what I'm doing is I'm telling you that 1 plus epsilon to the negative 1/2 power that's what I want to do. I don't know. No, I don't want to do that. What do I want to do? I actually want you to figure it out. Okay, so can you guys actually figure out what value of v does this work for? So you can figure out gamma. You can figure out what the gamma should be by doing it exactly, right? 1 over the square root. And then can you put it in here and see, does it give you the same response? What value of v does this mean? Does this work for? And so the answer is going to be v less than some answer. If you're less than something, there's some maximum v where you would say this is kind of working. If you go above that, it doesn't work so well. But if you're less than this, then you're pretty sure it's going to work. Anybody know what I'm talking about? Should we try something? Can I try something? What do you think it might be? What value of v do you think might work? Can we get a guess?
0.
What's a guess?
Something less than the speed of light.
Well, that's not very useful. Okay. No, we got to go slow. Okay. The idea is to go slow. So what does it mean?
So 1 velocity equals 0.
Well, that's really slow. That's obviously going to work because this is gone. Can we get an answer that's reasonably slow, but maybe not so slow that you
1
just
meter per second.
Huh?
Is 1 meter per second too slow?
Yeah, pretty much. It's not. It's not really interesting. Now, I wanted to actually ask you if maybe 0.1 c is small enough. Okay, that's still pretty fast in human terms, but I would like you to consider, does it work? So let's find gamma, find the value, and then compare it to this value of gamma, the approximate value, 1 plus v squared over c squared, 2c squared. Can you compare it? What's the value of gamma for 0.1 c? So can you
Derive it.
what'd you get? Put some more numbers in here if you want. Okay, but let's get like to 3 significant figures or four significant figures. Here we go. I got 1.005. Okay, when I put it in. Did you guys get a number like that?
Yeah, that makes sense.
Okay, so now what do I put here? I got 1 plus 0.1 c squared over 2 c squared, the c squared. So what do I get? And I got 1.005. Okay, do you guys see? Are you following? I got the same answer.
Yeah,
Are you confused or are you okay with this?
that makes sense.
Okay, so it turns out that this is actually slow enough. This is slow enough for our approximation to be true. It's not very slow actually, right? If you're going 0.1 C, you're going faster than any human thing that has ever gone. Any human thing. I mean, that's, I don't know, depends. Any human, how about that? Any human. Way, way faster than any human. Okay, but not faster than we can make particles go. Obviously, we make particles go much faster than that. But the point is, when can you apply this situation? I found 0.1 works. What about 0.2? Maybe I should have just, let's try 0.2. Does 0.2 work? 0.2C. Let's try that. 0.2C. Hey, does it work?
Okay, it just becomes 1.01.
Well, that's the approximation, but what is the gamma?
Wouldn't I think it's the same thing for the gamma? No, it's less.
What'd you get? So I got a gamma of 1.02. I'm going to put a couple more digits just to put it in, okay? Because I see this, I probably should have changed it to a 1, right? But if I use the approximation, I get 1 plus 0.2 squared C squared over 2 C squared, is that point? I get 1.02. So now if I want to keep one more digit, 1.021, it doesn't agree, right? So it agrees to 3 significant figures, but not to 4, right? So this one agreed to 4 significant figures. That was pretty good. But this one is only 3. So what do you notice, right? It depends on the number of significant figures. How carefully are we measuring our speeds, right? If it's very careful, we may need to go a little bit slower to get for this condition to work, right? It may be that it doesn't quite work when you go at 0.2 C. But if you only need 3 significant figures, yeah, this agrees to 3 significant figures. If I ignore that last digit, which I can, it works great. Okay, what about 3.3 C? Try that one. You understand what I'm trying to do? I'm trying to see, like, in what scenario am I going to need to use this, and how stringent do my speeds have to be, right? So 0.3.
How are you getting that exact gamma answer?
I'm doing 1 over the square root of 1 minus v squared minus c, 1 over 1 minus v squared over c squared.
Okay. Oh, I see. Yeah, the square root of, okay, you're using that, and then you're using this new
I'm
gamma
actually, yeah, and I just want to see, do they match or not, right?
I see.
So I know that I could do this math, it's not hard, but I wanted to use this expansion because sometimes, I don't know why, because I don't know the speed. I don't know what it is necessarily. I'm trying to come up with a new formula that might work, even if I don't know the speed. So I got a number 1.0483, okay, 4 significant figures. And so this one, the gamma is 1.02. Where'd you get 5 significant figures, Tom? Gamma is 1.0206. Did I do it wrong? Maybe I did it wrong. That's fine. Okay. 0.2 squared plus 1 square root shift inverse. I got 1.0206. Okay, so I'm still getting the same answer. I'm getting a different answer than you on 0.2. Point C, I got this, but when I use gamma of 1 plus
Approximation
v squared over 2c squared, I get
1.045.
Yeah, so you can see it it doesn't work anymore, right? If I round it to 3 significant figures, it's not correct. So, oh yeah, it is. Sorry. To 3 significant figures, it's fine, but not to 4. Sorry, the gamma that I'm disagreeing, you put 1.002. I got 1.0206 for the actual gamma for 0.2c. And then I got 1.02 exactly for this approximation. So they agree to 3 significant figures, but not to 4, right? If I round this to 4 significant figures, I have a 1 here, which does not match. And the same thing with this one, right? It works to 3 significant figures, but not to 4. Well, what about, so if I only need 3 significant figures, it turns out this is slow enough and it'll give me the result. You know, that's reasonable. Okay, 0.4, how about 0.4c, right? Just to see when does it stop working, you know, to 3 significant figures, for example. And at that point, I probably don't find it as useful to do this approximation anymore.
I see. So as you get closer to the speed of light, it becomes less relevant.
Yes, well, it stops working so well. So I got 1.0911, right? 5 significant figures. But when I do the approximation, what do I get? Okay, I get 1.08. Now it doesn't even work to 3 significant figures. Okay, so the faster I go, the further it deviates from the real value. Okay, and so, but anyways, it looks like if I only need 3 significant figures of precision, that it works pretty well all the way up to 0.3c. That's very, very fast. It's very, very fast. And 0.4c, it stops working, right? It just doesn't, they don't agree. To 3 significant figures, they don't even agree. So I wouldn't do it. This approximation is not good anymore, right? It's not useful to me. If it doesn't agree, then why am I using it, right? I want to use it as long as it works. And so we showed that it works at 0.1, 0.2, all the way up to 0.3 if you only care about 3 significant figures. If you need 4 significant figures, then you have to be going less than 0.1c, and then it still does agree. Okay, so we see that there's a regime where this approximation works. And now let's try to jump to a new problem. Okay, so what I want to talk to you guys about is this idea that we actually have a problem with matter cannot move at the speed of light. I want to talk about why, right? Why would that be? This is something, it's not a fundamental idea that Einstein posed. It's a corollary, right? It's one of the manifestations of special relativity that occurs, right? Why is it that matter cannot move at the speed of light? And there's a couple of ways to approach this. But why don't we start off by, let's start off with the energy formula, right? E equals mc squared, or E equals gamma m0c squared. And I want to talk about gamma. What happens to gamma if v equals c, right? So 1 over the square root of 1 minus v squared over c squared. So what happens to gamma? If v equals c, what happens to gamma? In the limit as v, so now I would use a limit. In the limit as v approaches c, what happens to gamma? Anybody on the YouTube? Infinity, that's right, okay. Nobody's on the YouTube. Okay, everybody is here, okay. We're missing like half our class, more.
Does it just
okay,
become 1 over 1?
Huh?
Does it just become 1 over 1?
No, it's 1 over 1 minus 1.
Oh yeah, so that's the square root of 0 does not exist in the denominator.
Yeah, we got a problem, right? You get infinity. Infinity. I love infinity, don't you? No, I don't. I don't love it. Actually, in physics, I want to tell you, this is a pretty important idea. In physics, if you get an answer that is infinity, you screwed up. Okay? There's a mistake. It can't be. You can't get infinite. What does it mean, right? What does it even mean? Infinite energy, equals infinity. That means all of it, right? Infinite. Well, it doesn't mean all of it, I guess. Infinity, yeah. Yeah, you blew it. You screwed up. Okay, so energy that is infinite, that's a problem, right? We don't like that. That's bad. Okay, so anyways, back to the question, how would you even do that, right? How would you speed up a particle from a slower speed up to the speed of light, right? Well, you got to push on it, right? Remember, this is our formula, classical formula, F equals ma. It turns out that Einstein not changed it, but actually went back to the original problem. This is not the original Newtonian equation, by the way. In fact, F equals dp dt. I know we're not a calculus-based class, but you see the P right here? That's momentum, right? It's the rate at which momentum is changing. And so Einstein actually used the same equation. So the relativistic form is all about momentum. And so if you stop and you think about it, remember that momentum, which is gamma mv, right? Kind of like that. It's really what's going on is this is the effective mass. This is the mass of the particle. And if you push on something, remember that this is the inertia, right? The mass is the inertia. So what happens when you start pushing on something and you make it go faster? It has more mass. And if it has more mass, it has more inertia. So what does it mean? The faster it goes, the harder it is to change its motion, right? The harder it is to change its motion. So the larger the velocity, larger the v, the larger the mass, the greater the inertia. The harder it is to change it. And the concept would be that if you went if you went the speed of light, you would have infinite mass, which means that it's infinitely hard to move it, which means you can't move it, right? So basically, the faster you go, the harder it becomes to make any changes in the motion of that particle, that mass. So it is not possible. So that's basically what we end up with, right? It is not possible for matter particles to move at the speed of light. Okay? So that's the truth. That's a fact, because you can't have infinite speed. Oh no, matter or antimatter. I meant massive particles. Okay, mass. Particles with mass. Matter and antimatter both have mass, so it doesn't matter.
So wait, Sean,
It does matter.
What are photons then? They're just electrons?
No. Okay, good question, Kenny.
Why are you writing my name?
What? I want to write this down. I don't know, because I was just thinking about that. Kenny asks, what are photons? Well, I'm going to ask you. Do they have any mass?
They don't.
They cannot, right? They are massless. Yeah, Tom put EM wiggles, electromagnetic waves, right? They're electromagnetic waves.
Okay, they're
waves. Photon is massless. A photon cannot have mass. Otherwise, it couldn't move at the speed of light. So photons must have mass. What about these things called neutrinos? Has anybody heard about those? Neutrinos.
Those have mass of some kind.
They do. They have very tiny mass. And actually, it's a research question. How much mass do they have? Right now, the best that they do is put an upper bound on the mass. In other words, they know that the mass is less than a quantity, right? So actually, I'm just curious. Let's you guys want to search with me? Let's have some fun together, right? Let's see. I'm just kind of, let me learn with you. I don't know the right answer. I mean, I don't know what it is. Okay. But I put in here in my Google search, neutrino mass, right? Neutrino mass, okay. Nature, I like nature. Nature's a good place to go. Let's see, okay. All right, yeah, let's do this. Let's see, they're trying to show you, this is September 17th of last year. That's pretty recent. The maximum mass, right? Morphing neutrino, oh man, neutrinos are fun. Oh my gosh, does anybody even know what this means?
Oh my God.
Do you know what that means? Oh no, here, sorry, this is it. This is amazing. What the heck?
Electron volts?
Yeah, what the heck? Anybody know what that means? Christian, you might know what that means, huh? Anybody? No? Okay. Would you like to know what that means? I would like you to know what that means.
1 electron?
Yeah, I would like to know what that means. Okay, so but right here, they are also the lightest of all the known subatomic particles that have mass weighing 500,000 times 500,000. That's cute, right? I wonder why. But they tend to cross matter undetected, right? So according to this, this is the reference. So actually, we should read some papers. Would you guys like to do that as part of your class?
Yeah.
Wouldn't that be kind of fun? There's
Definitely.
some cool things to look at. And then you can click the PDF and you get a free version of it here. Oh, look at all the people. An improved upper limit on the neutrino mass. This is a team collaboration. Oh my gosh. Look at all the people. That is awesome. Okay. And then you get down and here's the abstract. And they write a 1-paragraph thing where they summarize all of their results. This is the most important thing to read. Before you read the paper, make sure you read the abstract. Okay. So we report on the neutrino mass measurement result from the first 4-week science run of the Karlsruhe tritium neutrino experiment, Katrin, in spring of 2019. Beta decay electrons, oh my God, I want to talk about that too. But anyways, from a high purity gaseous molecular tritium source are energy analyzed by a high resolution MAC-E filter, whatever that means. I have no idea what that is. A fit of the integrated electron spectrum over a narrow interval around the kinematic endpoint of 18.57.
Kilo electron volts?
Yeah. Kilo
So wait,
electron volt. Yeah.
electron volts are tiny.
They
volts.
are tiny, and actually their amount of energy, but we'll get back to that. Yeah. So it says from this we derive an upper limit of 1.1 electron volts with a 90% confidence level. That's pretty cool. So they are 90% sure, right,
Oh wow,
that it's less than 1.1 electron volts. Okay, so now you can look at the experiment. It's the big deal.
so Sean,
Yes.
1 electron volt is equivalent to 1 to the negative 18 volts.
Negative 19.
Yeah.
One times 10 to the negative 19 joules, right? 1.02.
That's very small.
It's very tiny. Yeah. Actually, I do want to cover that. That's actually one of the topics that I have in mind to talk to you guys about. So you can read this and go, wow, okay, cool. So neutrinos are tiny, and the energy of a neutrino, we just found out, and I didn't know this before you just found out, is with a 90% confidence, less than 1.1 EV. That's called an electron volt. That's a totally different topic, which I would love to talk about, but let's talk about it on another day, okay? So that's tiny. This is tiny. So, but these ones travel at nearly the speed of light. In fact, actually electrons can travel near the speed of light too, right? Electrons can travel at nearly the speed of light. And actually, where have we human beings made electrons travel the fastest? And the answer is, again, at CERN, right? At CERN. The CERN has made electrons and protons travel at closer to the speed of light than anything that you can imagine. I mean, it's kind of mind-boggling how fast they go.
Are people still worried about a black hole being created, a mini black hole being created?
Yeah, that was one of the ideas. They were, you know, a little bit concerned. What happens if you make a black hole? And the concern was, you know, that it would destroy the Earth. But if you study black hole thermodynamics, you find out that
It would radiate away, right?
black holes will just evaporate away if they're that tiny. Yeah, so they don't really, but we don't know how they do that actually. One of the questions, so we don't think that they've ever done that, by the way. It's pretty difficult to make a black hole.
Yeah, I think so.
I actually accidentally did the one the other day, but I'm like, no, it's not. Yeah, I don't know how to do that. Humans could even do that. So what are we talking about? Oh yeah, photons. Okay. So photons don't have mass. They can travel at the speed of light. Actually, anything that is massless. What else can travel at the speed of light then? Oh, actually, I did want to tell you this number. Sorry. What is the fastest electron? Fastest electron. Fastest man-made object. No, that's not true. Fastest electron. Electron. What's the fastest electron? Oh my gosh. The highest electron speed ever created. Oh, I don't know. That's crazy. Okay. So according to this, I don't know if this is really right. The fastest electron speed. This looks, they said that a large electron positron collider, LEP. I want to see, I think this must be at CERN. It must be. The acronym is LEP. Says here that the electron was accelerated to 0.99999. No, this can't be right. This can't be right. This is quora.com. This can't be right. It's not right. It can't be right. Oh my gosh, it's right. It is right. Oh my gosh, it is right. Okay, I gotta count the nines here. Sorry, it's a lot of nines. Is this right? This can't be right. It says it. Oh my gosh. That is, no, this isn't right. This is not right. This is not right. Let me just, I can't believe this. You got a question. Oh my gosh, it said it again. Okay. The fastest, where is LEP? Okay, you guys want to search with me? Do you know? Oh, gluons move at speed, gravitons. Yeah, probably. Well, actually not maybe. I mean, the gravitational waves move at the speed of light as well. Yeah. Speed of light, okay. I don't know, accelerators, got it, okay. What is the fastest? I just want to current, oh, LEP, look for LEP. Do you see LEP? Where is the LEP? Oh, this is, okay. Okay, this is CERN, okay, cool. So the Large Electron Positron Collider was and still is the largest electron positron accelerator. Oh, it's not proton. Oh, it's positron, right? Okay, that's great. Okay, and they made it to, oh my gosh, that's just crazy. Okay, all right, so here's, it looks like this is the answer. Okay, so it looks like it made up, do you see here, the top energy was 209 GeVs. Let's see if this is really right. Okay, so when I looked it up, I got this result here. And actually, okay, so that must be it. Oh my gosh, look at, do you see this number? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 nines and 2 eights. Okay. Do you see that, right? So you can't go the speed of light, but you can go pretty darn close. Okay, so that is amazing. Okay, that's actually, okay. So that was 104.5 GeVs. That was the energy. Okay, that was the energy. So that is pretty remarkable. And then what happens if you smash two of them together? You get a total energy of 209 GeVs, right? Does that make sense? Now, it turns out that CERN right now is also trying to do proton collisions. And they actually have a record for that, which is quite a bit different. So what's the difference between protons and electrons? They have much more mass. What the heck did I wrote? Proton. I don't know what I wrote. No, proton collisions. Proton collisions, protons have much greater mass than electrons. And it turns out that right now, the maximum speed proton, I think it has about 8 nines, facts and figures. Okay, the Large Hadron Collider. You guys can't see my screen, sorry. Let's go back to, I'm back to CERN again. What is the speed? Main goal. What is that? Okay, here we go. Here we go. This is the nominal energy. You see the numbers now? So actually we'll eventually figure out how to do this, but this is the energy per proton, right? 6.5 TeV. Does anybody know what the capital T stands for?
Tera?
Tera, that's right, tera. So how does it go? Let's see. So 10 to the 6th is mega. Okay, do we want to write this down or do you know this? 10 to the 6th is mega. 10 to the 9th is giga.
Oh, giga, yeah.
And 10 to the
12th.
10 to the 12th is tera. Right, Tom?
Brilliant,
What do you go? What's 10 to the 15th? 10 to the 15th has another name. Anybody know that one?
Peta?
Peta, right. Is that peta?
Yeah.
Peta? And what's 10 to the 18th?
Exa?
Exa, okay. Right. Okay, great. Okay, so, but anyways, this is, if you can take a look, right, before we said GeVs for the electron, but with the proton, they've gotten to the TeV range. And so this is an incredible amount of energy, incredible amount of energy. I'm kind of getting off on a tangent. What did I want to talk about? Oh yeah, I want to talk to you guys about something very interesting. But it's kind of like a different topic, but anyways, it's okay. It has to do with energy and relativity and all this cool stuff. But yeah, okay. So actually, maybe we can come back to this again for a second. So a photon does not have mass, right? Okay. Does a photon have momentum? So we know that in the classical picture of momentum, photons would not have momentum. But maybe part of the way to understand this is, yes, okay, so Tom put down a solar sail. Yes, okay. I've heard of this thing called a solar sail. Okay, how does a solar sail work? The idea is if you want to sail away from the star, Sol, right? You make a spacecraft with a giant sail, right? I'm sure I'm not drawing a very good picture, but, and you put the sail out here and the light reflects off of the sail and pushes you away from the star, right? You literally get pushed by the light. And it turns out we've seen this happen with comets and asteroids, right? The sunlight reflecting off of the surface changes just slightly the movement of an object, right? It can change its rotation and it can actually change its linear motion as well. So that's evidence for you. So the answer is yes, right? Yes. A photon has momentum. So how does that work? How does a photon have momentum? It doesn't have it with mass, right? Momentum is something somehow different than what we've described before. And so let's talk about this thing called, how does a photon momentum work, right? Photon momentum. And so actually that's a good question. Did we talk about photon energy before? We talked about photon energy, right? Did we talk about photon energy? First talk about energy. Yes, okay. Does everybody remember this? This is Planck's constant. And then multiply times the frequency. So this is the energy of a photon. Have I talked about this before in this class? I don't know if I did.
No, but we're learning it in chemistry right now.
Okay, so let's go ahead and write this down then. This is a photon energy. Is this Planck's constant? And then this is the frequency. We have talked about frequency. I know we have talked about frequency and wavelength. Planck's constant is just a constant, right? You could go look it up. Anybody know the number?
6.626.
6.626 times
10 to the -34.
Negative 34.
Yeah.
Okay. Joules times seconds. Okay. So H is a very small number. And so frequency is how it works. Okay. So you can kind of like, you can talk about the energy of a photon, and that's fine. But, where does the momentum come from? And so it turns out that Einstein came up with an idea, and actually I'm not going to show you where this comes from, huh? I guess I'm going to go ahead and just tell you. So Einstein was able to describe the something very interesting. Very interesting. Oh, I should just show you. Let me show you this. Let's talk about kinetic energy again. So we know the formula. What is it? It's 1/2 mv squared. Oh, that's not Einstein. That's classical. Sorry, classical. Sorry, I want to talk about it again. All right. But let me show you something else. It turns out you may not have ever seen this before, but another way to write the kinetic energy is p squared divided by 2m. Does everybody see that works? Everybody see that? So, okay, yeah, so you just go mv squared over 2m and you get 1/2 mv squared, right? You get the same thing, check. Okay, sorry, lights, okay. So what he said is there should be something analogous, right? In fact, maybe it's the momentum that I should really be talking about. The momentum is going to give me my kinetic energy, thinking about it like that. So actually, I'm just going to jump. I'm going to tell you what he said. So Einstein said that the energy of let me just do mass. Oh shoot, let's do massless. massless particle. The energy of a massless particle is P times C. Okay, I'm just going to give it to you, right? P times C. So this is supposed to be for things like photons, right? Things like photons. So using this equation, you can kind of invert, right? You can invert, and you can come up with a momentum equation, right? The momentum is E divided by C, right? That's what it is. So E, by the way, was H times F divided by C, right? So do you see this kind of funny thing here? You guys see the F and the C? Do you remember that C equals F times lambda? Anybody remember that? What's C divided by F then? Lambda, right? So I don't have C divided by half, I have F divided by C. So it turns out it's the same thing as H over lambda. That's funny, right? That's cute. Cute. So massless particles can have momentum that's based on their frequency or on their wavelength, right? Directly proportional to the frequency or inversely proportional to the wavelength. So photons have momentum, which is greater when their energy is greater and smaller when their energy is smaller. Or thinking about it in terms of wavelength, the shorter the wavelength, the greater the momentum of the photon. So actually, something really crazy happens. It turns out there is an effect. Actually, wow, how did I get here? I don't know how I got here, but I got here. This is great.
I think it's my fault.
No, I wanted to go here. This is my joy. I'm so happy. I'm so psyched. This is so exciting. Write this down, Compton effect. This is a beautiful, amazing example of photon momentum, okay? So what I'm gonna do is I'm gonna put a squiggly thing here. This is the incident photon, okay? And it has a frequency, and it has a wavelength, right? It has a frequency, it has a wavelength, it has an energy, a frequency, a wavelength, right? And the idea is that it's going to scatter off of a stationary electron, right? So the Compton effect, a photon collides. We don't really call it collides, but it turns out you're basically describing something that looks like a collision. It doesn't really collide. What's the right word? Scatters off of an electron. So the electromagnetic wave interacts with the electric charge. And what happens? So this is your before picture. Okay. You'll notice that the photon is traveling in this direction. So if you remember, momentum has a direction, and therefore the momentum is in this direction. So after something very beautiful, right? You'll see the electron moving off with some velocity. It's moving, it's scattered, right? Where is the photon going to go? And so this is a kind of an important concept, right? You have the concept of conservation of momentum. And whether it's relativistic or not, this is true, conservation of momentum. So does the photon keep going? And the answer is it can't keep going, because that would leave us with momentum that is not just horizontal. Okay, so I apologize because I'm going to do this kind of quickly, But if you analyze the velocity of the electron, you can see it has a horizontal piece and a vertical piece, but there wasn't a vertical piece when I started. So this thing can't be here, but it is, but it can't be, but it is, right? So what does it mean? It means that the photon has to scatter in this direction over here. It has to scatter. This is the photon, right? This is the scattered photon. The final photon, right? The scattered photon. Okay. And in this way, because its momentum has, again, it has a piece that is vertical and the vertical pieces have to cancel somehow. I know I haven't drawn it to scale. So the amount of photon momentum has to balance, right? And so the vertical piece of momentum here has to cancel the vertical piece here. Again, don't worry too much about that. But anyways, the other thing that we have to have has to still be true is conservation of energy. That has to still be true in this frame of reference. So if I tell you that there's a scattered energy and a scattered frequency and a scattered wavelength, what can you tell me? Is the energy of the scattered photon bigger, smaller, or the same as the energy of the incident photon? And why?
It's going to be smaller because energy is transversed into the electron.
Okay, actually, can I just, it's got to be smaller, right? E is smaller. I can just write less than E, right? It has to be, because the electron has some of the energy now.
Exactly.
The electron has energy that it didn't have before. Okay, Tom asked the question, what if the electron goes to the left? That is impossible, Tom. Thank you for bringing up an impossible situation. It is not possible. Okay, so we will never see an electron scatter backwards. It just doesn't happen. It can only scatter in the forward direction somehow. Okay, so, but it can be nearly 90 degrees, but not 90 degrees. It's not even possible to do that. Okay, so this is true. So what about the frequency of the scattered photon? What can you say?
It decreases, the frequency decreases.
Pardon?
The frequency must decrease in...
Must also decrease, yes, that's right. And what about the wavelength?
Must increase.
Must increase, right? Because longer wavelength is the same thing as lower frequency. So longer wavelength is the same thing as lower frequency. That's called the Compton effect. So the wavelength of the photon changes after interacting with the electron. The electron takes away some of the energy of the photon. That's kind of simple, easy. This is just we're not doing the math, even though I actually think it'd be fun to do the math. I think it's too much of a tangent. I want to talk about some other things, but I do want you to think about it. And do you want to do any math? I mean, actually, if you want to, I'll do it. You want to do more math? We can actually try to consider a real life problem if you like.
Sure.
Wow. You guys have to stop me when I go too long. It's already, look at what time it is. It's already 11:15, 11:20. All right, so raise your hand if you want to do the math. You guys actually have this thing, you can go yes. You have in your participation, by the way. I don't know if you guys know you can do that. You raise your hand. You can go yes, no. Anybody want to do the math or no? Actually, I have so many things. Let's do something else. I just wanted you to see the concept, right, conceptually. Otherwise, you want to do it. Oh, Johnny wants to do it. Okay. Are you raising your hand, Johnny, or you say, yes, I want to do it?
Tom doesn't want to do it.
You do want it, or you don't?
I don't think Tom does.
Okay. It's a little messy. You want to do it. Okay. All right. Well, why don't we do this? Let's take a little break right now. It's okay if I don't. Okay. All right. So why don't I leave it, because there's some other things that I want to talk about with you, and I think it's actually really fun, but it is really going to get us into another realm. I mean, I could just do an example. How about that? I could do a quick example, maybe. You could say, what happens to a photon energy if the electron scatters at an angle of 30 degrees to the incident photon? Can I just do a demo problem for you? And then we'll move on from there. We'll just take that. Okay, why don't we try that? But let's take a break right now. So I'm going to give you a 15-minute break. Use the bathroom and do whatever you want to do. But let's take a break, and we'll come back and do more math. Okay? So thank you guys. And then I have to figure out what I'm going to give you for problems. We didn't even get to a topic I was supposed to get to, but this is a really cool topic. I like this. This is really interesting. So photons interact with matter. Okay. And this is actually one of the ways that they can do that. Okay. All right. We'll take a 15-minute break. So come back at 11:37. Okay. All right. I'm going to go to the bathroom myself. So I'll be back. Hey, Tom. You were so Rutherford was surprised by, but actually Rutherford didn't use electrons. What did he use? Anybody remember? The gold foil experiment. Alpha particles, right? So, so the electron. Okay, so the photon can bounce backwards. By the way, that's actually still possible. So the photon can bounce backwards, right? It is possible to bounce straight. That's actually a pretty. In fact, that's a pretty.
Well,
cool
isn't
idea.
that what would happen if you had a solar sail?
Well, it's not bouncing off an individual electron, it's bouncing. Actually, wow. Let's think about that. Actually, wow, okay. This is a pretty fundamental idea in physics. Maybe we should talk about it before we do this. Oh my gosh, you guys want to do too much. There's not enough time in life. Okay. Actually, if you ask the question, which one delivers more momentum? A ball, like a ball of clay with a mass and velocity that smashes into a thing and then, you know, splats on the surface, or one where you take a rubber, a bouncy ball, and you bounce it, right? So that it hits and then rebounds with a bigger, you know, with the same velocity or slightly smaller velocity. Which one will hit with a bigger force? Which one will exchange more momentum? And so the question is, well, what is the change in momentum, right? And so momentum is mass times velocity. In this case, you have a positive momentum. Let's call it positive. And then the afterwards, you have zero momentum. So the change in momentum yeah, no. So the change of momentum goes from positive P. Oh, sorry. Well, how do you find change of momentum? It's the final momentum minus the initial momentum, right? So you go 0 minus P, you get negative P. That's the change in momentum. But in this one, let's say you go from a positive P and then it bounces backwards, you got negative P. What's the change in momentum? Well, now it's negative P minus P. It's negative 2P, right? The bigger change in momentum. So when something bounces, it pushes, it actually delivers more momentum to the object here than it would here. There's a bigger change in momentum on the object, which comes from, actually, you can't change the momentum of the system, right? So what happens here is, what is the momentum that is gained by the block? Well, if the clay loses the momentum, the block has to gain that much momentum, right? It has to have this much momentum. But in this situation, if you have negative P, then this block has to actually have a positive 2P, right? Positive 2P, negative P makes positive P, the original momentum. So the block gains more momentum when you bounce an object than when you hit it and smash into it and stop, right? So when a solar sail reflects light, right, then they actually get a positive momentum, not just the original photon's momentum, but double the photon momentum when it bounces. So bouncing is better than bouncing delivers a bigger kick. Reflecting delivers a bigger kick than absorbing. Okay, so unless you want to use that light energy to heat you up, then reflecting it gives you a bigger effect on your momentum. Okay, so you guys wanted to do the Compton effect, and I looked up on Wikipedia the equation, and there's no way I'm going to have enough time to do this. I remember it now, but I'm going to go ahead and show you the Wikipedia page just so you can look at it and try to. If you want to do it at some later time, I'd be fine to do that, but I think there's not enough time today. So let me just show you the Wikipedia page. Okay, it's called Compton scattering. And actually the way it worked was slightly different than I described it. It says that the electrons are scattering off of a piece of metal, right? And the electrons are inside of the metal, something like that. Or graphite, I don't know, something, I don't know, whatever. Don't worry about that. Okay, so the idea is, here's the original story. And so there's a wavelength coming in, it scatters the electron, and then there's a wavelength going out. And we know that the wavelength going out must be longer than the wavelength coming in because it gives some of its energy to the electron. And so it has to have less energy, it has to have a longer wavelength. And here is our formula. So yeah, so this is, this would be a little bit of work to derive this. And the reason I'm going to avoid it is because you have to do two things simultaneously: conservation of momentum and conservation of energy. But we can derive this. I mean, it's derivable. There's a couple of things that you want to be able to figure out. But it turns out that there's an angle dependence on this, right? So the scattering of the photon and the scattering of the electron are going to be related to each other, but blah, 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 blah. Okay, so we're not going to do it. But anyways, I will do it if you're interested, or maybe I can figure out a way to share with you the derivation, but a little bit of a mess. So this is the lengthening, right? It's getting longer. So you're going to subtract this from this and get a positive number, and it's equal to this quantity times 1 minus cosine theta. Okay, so we're not going to actually do it today. We got just a conceptual idea, but I do want to talk about a couple of ideas that kind of go along with this. In order to derive this, we would actually need to talk a little bit more about the electron energy, right? So I know I wrote down before E equals gamma mc squared. That's true. That's not wrong. But Einstein actually did something else, and he showed that, yeah, you remember he talked about space and time being connected? Well, he did something very, very interesting. He said that the energy squared, maybe you could write this down for me, of a massive particle is Pc squared plus mc squared squared. So I know at least some of you will look at this and maybe see the Pythagorean theorem, which is great. And that's great, actually, that's fine. In fact, think of it that way if you want. But it turns out that that definitely seems to be the way it works, right? That the energy of the particle, even though this is true, if you try to include just a momentum component, it doesn't come in a single term. It comes in like this. So the energy would be the square root of this quantity, right? P squared C squared plus m0 squared c to the fourth, right? This whole thing. But if you look at this right here, the concept is that the energy has two components to it, right? It has this PC component, and then it has this other component, which is mc squared. And then the energy is somehow, the resolution of this. And that's interesting. So let's just go ahead and I know I'm not explaining where that comes from, but this is in fact the equation that Einstein used to describe massive particles. Okay, so I know this might not be smooth, but I want to see if we can get to an idea that you guys saw before. We saw that the momentum for a photon was P equals H divided by lambda. Okay, that's interesting, right? So lambda is something that we understand, that's wavelength, right? But if I rearrange this, there was a very famous fellow by the name of de Broglie, and he wrote it down just a little bit differently. He says, well, what about lambda? How does it relate to momentum? He says, lambda equals H divided by P. And you're like, well, why'd you do that? That was just circular, right? Except de Broglie says should work for matter as well. He said, what if this is true for matter as well? He says, what if there's a wavelength for matter, right? So a photon is both a particle and a wave, right? But what about matter? And it turns out that de Broglie was able to prove or show mathematically that you could at least think about it that way, that matter is a particle and a wave. And so this is kind of a curious phenomena. And when we think about how we see things, right, with light, I'm particularly interested in a telescope, for example. One of the concepts in telescopes, if you talk about a telescope has a concept called the angular resolution. The angular resolution of a telescope. And actually, I went and got the Wikipedia page just because it's easier than I don't have prepared material, so I'm talking about this. Angular resolution is the ability of an image forming device, such as an optical or radio telescope, a microscope, a camera, or an eye, to distinguish small details of an object, thereby making it a major determinant of image resolution. I don't know what that means, whatever. The closely related term spatial resolution refers to the precision of a measurement with respect to space. Okay, so I'm not going to deal with that. I'm going to just stick to angular resolution. And just, thinking about this, right? If I have two stars, right, that are very close together, kind of like two headlights on a car, right? If I'm on the highway looking at cars that are very distant, I can't actually see that they're two. They look like just one big spot, right? And then as the car comes closer, I can finally see that there's two headlights, right? And so the idea is if you're far away, when you look at these two things, right, the angle is too small, right? You can't see that. But as you get closer, right, the angle between them gets bigger, right? So the angle that I can perceive two objects as separate is kind of the special angle that I'm thinking about. We call it the angular resolution. So the angle at which I can distinguish two things as being two separate things. And it's dependent on, on a couple of things, right? So what is it dependent on? So back to the screen share. Okay. So blah, 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 blah. Okay, there's the picture. All right, that's a great picture. Okay, so there's far away. And then as I get closer, finally, I can see two separate objects. So it turns out it has to do with this thing that happens to light. When light goes through an opening, it spreads, and that's called diffraction. And if this is a circular aperture, which is, you know, pretty much the case for your eye and for telescope, this is the angular resolution in radians. Now, it turns out, I don't know why is it simpler for a single telescope? I don't know why it's easier, but oh, it's approximated. Okay, I got you. It's approximation. Okay, so in other words, the key part that I want to use is the lambda and the d. So actually, let's just, you have the actual thing, but actually we're going to do the approximation, right? The approximation, which is pretty good, is that the angular resolution is the lambda divided by d, right? So the wavelength of the, you know, the light, and d is the size of the telescope, the diameter of the telescope. And what it means is that if you want this to be small, which means have very, you know, high resolution, right? High resolution means lots of detail, means theta is a small number. If you want this to be small, then what do? Well, use a big telescope, a bigger telescope, right? That's one of the answers. If you're not going to be able to probe different wavelengths, then making a bigger telescope automatically gives you a smaller angular resolution. By the way, this is measured in radians. Okay, but there is another answer. It turns out if you use a different wavelength, you can get better resolution too. So by using a shorter wavelength, we get better resolution. So in terms of visible color, you know, Roy G. Biv, which color gives you the best resolution? Right, the violet. So violet has better resolution. Better, I mean, better is a quality statement, but it has a smaller theta, right? So it should show you finer detail than red. That's interesting. And in fact, it's an interesting thing, right? We can get, a picture can be more detailed if you look at a specific color instead of having a mix of colors. You can actually see more detail. So that's neat, right? And it turns out it applies to things like microscopes as well. Similar kind of concept. So you can either make it bigger or you can use a smaller wavelength. Now, if we're talking about microscopes, right? Microscopes, then it turns out that you can't make them very big, right? I mean, usually there's a limit to how big you can make them. So it turns out that we went the other way. We really talked about lambda. How do we make lambda small, right? Small. How do you make lambda small? And so you might know that there are visible light microscopes, right? Visible light microscopes. But there are actually more higher resolution microscopes, right? We have microscopes that can see down to the atomic level now.
I used to work on a scanning electron microscope.
Yes, awesome. Okay. I was hoping some of you had that experience. So electron microscope. An electron microscope. What is an electron microscope?
There's a beam that is emitted through.
So let's just, sorry, one at a time.
A corner someplace we'll be testing, but I think Deborah speaks.
Hello.
I didn't quite hear that.
Oh, there's a beam. There's a little tungsten element that gets hit with a high voltage, and it creates a beam of electrons that gets passed through a set of filters and directed through magnets.
Okay, so you're pretty close, but actually I'm gonna help you get even closer. So it turns out that the electrons are emitted by making it hot. They just jump right off of the metal. So you make that tungsten filament hot and the electrons jump off. And then, Christian, that voltage is going to do something really important. What is it going to do? Anybody know? The voltage, it's going to speed them up. It's going to accelerate them. And so it turns out that electrons can be used because electrons have a wavelength. And de Broglie told us the formula. How do you get the wavelength of an electron? It's h divided by p. This is the momentum, right? So which momentum do we use? The classical or the relativistic? Well, depends, right? It depends on how fast it's going. If they're non-relativistic, you can just use the non-relativistic formula for momentum, but otherwise you need to use the relativistic momentum. Okay, so how fast do you have to be going before you need to use relativistic momentum? Anybody remember?
0.3 speed of light?
Yeah, something like that. So that's pretty darn fast. I don't know how fast that is, man. That's crazy. That's crazy fast, but we'll figure that out. We'll figure out what that means. Okay, so here's the question, right? If you go back to the diffraction, the angular resolution, lambda divided by d, right? This is not going to be changing. We can't control that. But you can improve the situation by changing lambda, right? So how do you make an electron microscope have better resolution? What do? And by the way, automatically, we're going to find out it has better resolution than any light microscope. But how do you get even better light microscope? Well, I mean, how do you get better resolution? How do you make lambda get bigger? Get smaller. How do you make lambda get smaller? This is a constant, yes, increase p, okay? The faster the electrons are moving, the smaller, the larger their momentum will be, and the smaller the wavelength will be. And so an electron microscope has the ability to accelerate electrons, this voltage that Christian was talking about. And actually, it's a topic that I want to cover. I don't think I'm going to have time today to cover it. But, you know, maybe. Oh, no, I still have something I didn't get to do yet. All right. But very soon, I do want to talk about it, because how do you make electrons speed up? How do you make them speed up?
Voltage, increase the voltage.
Yeah, so it's voltage, okay? So electrons, electrons are negative. A capacitor, great. Actually, thanks, Tom. That's great. So you put them between a couple of plates. That's called a capacitor. Not yet, sorry, it's not a capacitor yet. A capacitor is a pair of metal plates, a metal plate on the top and a metal plate on the bottom, okay, that you connect to a battery. Okay, so I'm going to ask you a question, and then you have to tell me which is which. If I want the electron to go this way, then do I want the bottom plate to be positive or negative? Which one? Positive, okay. So in electronics, a battery symbol is, or a voltage is, a long line and a short line, and the long line is the positive. Exactly, opposites attract, great. So the negative plate, this will be the negative plate because it's connected to the negative terminal of the battery or whatever voltage source. And the positive plate, this will be the positive plate. So the electron is going to be attracted to it. It's going to fall. And actually, it's something we haven't talked about. But electrons could care less about gravity. Does everybody know why? Why do electrons not care so much about gravity?
Because they're an electric charge, they're not a magnet, or because they don't.
One more time. They have electric charge, but
Yeah.
yes, they have almost no mass, right? So gravity cannot influence electrons very strongly. On the other hand, compared to their mass, the electric force is incredibly huge. Exactly. The electric force is much, much stronger. And so electrons don't fall the way the gravity points at all. They fall towards positives or away from negatives, right? They fall according to the electric field, not the gravitational field, right? So can I put that point down? Even if we're not covering it today, electrons fall according to the electric field, not the gravitational field, right? Gravity does not influence electrons. Actually, man, I don't want to talk about it. Shoot. Another thing, when you talk about things falling, by the way, and this is true, what happens to things when they fall? What does falling mean? Why do things fall? That's true, they accelerate. We think about it in terms of force. Actually, how about in terms of energy? Sorry, in terms of energy. Why do things fall? Why did my pen fall? Why does it fall, right? What happens to the energy? Well, the energy is conserved, but not all the energy, right? I mean, yeah, sorry, all the energy is conserved. Right, good. Exactly. So falling means losing potential energy and gaining kinetic energy. And so we'll talk about that maybe next class or something. Okay, so I don't want to get into that. But the idea is with an electron microscope, you accelerate the electrons, and the faster they go, the greater their momentum and the smaller their wavelength, which means your resolution gets better. And so, yeah, how does that work? Oh man, I'm not talking about this today. I gotta talk about something else. Because actually it's gonna turn out to be really easy to get relativistic with an electron. So before I do that, I wanna talk about, I'm just gonna jump to a new topic because I need to do it. Velocity addition. Okay, a velocity addition. Okay, and I really want to talk about relativity, relativistic. So we want to talk about what does it look like. So in standard classical physics, classical, right? Not relativistic. If I were, watching, I don't know, a plane. Let's make a plane, right? Got a plane, a big plane, right? Make it a big plane so we can see something going on. I have these windows, but actually I'm going to look through the side of the plane, and here's a wing right here, the cockpit. Okay. And I'm going to watch somebody. So the plane is moving forward. Let's give it a really big speed, maybe 15. I don't know if this is a big speed. Is that a big speed? 1500 meters per second. That's pretty fast. How about that? That's too fast. What's 1500 meters per second? Anybody? That's too fast, isn't it? What's a plane speed? What's a typical plane speed? Can anybody tell me a plane?
300 miles an hour becomes like what, 500 kilometers an hour? You want meters per second?
Yeah, let me do meters per second. What's a speed? How much? 500 miles an hour? 500 miles per hour? That's a reasonable speed, right?
Yeah.
So how do I convert it? 1 mile is 1609 meters. 1 hour is 3600 seconds. So what's that give me, right? You guys convert that? So 500 times, I got an answer, 10 miles per minute. Okay. 500 times 1609 divided by 3600. So 223. Okay. Yeah, so this was way too big. Okay, so 200. 200 meters per second.
That's
something
good.
like that. Okay, there's a reasonable number. And now I get a really good picture on the plane. And he's going to throw a baseball. And wow, he's going to go 100 miles an hour. And based on this, what would that be roughly? Like 40 meters per second. He's going to throw it. He's on the plane and he throws a baseball 40 meters per second. So if I watch from the ground, right, if I look up and I see the baseball, what do I see? How fast is the baseball moving? From my point of view, when I look at it, yeah, it's moving 240 meters per second, right? Because the plane was already moving forward. Even if he held it in his hand, I would see it moving 200 meters per second. And then he gives it a boost, right? And so you see 240. And, you know, and then somebody catches it and throws it back, right? Maybe this person throws it back and they're not quite as fast. It's only 30 meters per second. So when I see that ball moving backwards, what do I see? I don't see 30. What do I see? $170, great. So it's still moving forward 170 meters per second. Does everybody know how to do this, right? So the plane was forward 200. When you go backwards, you subtract this speed and you get 170. It's still moving forward, in other words, but not quite as fast as this one and not as fast as the plane. Okay, so this is all classical, but we have an issue with relativity, right? What's the maximum speed that anything can travel? All right, and the answer is speed of light. So I want to pose a problem for you, right? I'm on the Earth, right? I'm on the Earth, and I see a rocket, a big rocket, so I can see what's going on. Yeah, I see a rocket. And the rocket is traveling with a speed of 0.8 c, okay? 0.8 c, 0.8 c. And then I can look through the window and somebody's going to shoot an electron with a speed of 0.5 c, okay? And I'm watching from Earth. What do I see? How fast do I see? The answer is 1.3 c, right?
But isn't that not possible?
Yes, that's right. So that's wrong. There's no way. I can't see that. If I see that, that electron has more energy than the entire universe put together. Well, no, not more, equal to, right? Everything. It's not possible. Actually, I don't know what. Actually, you know what? That's a weird thing. I don't want to talk about it. But what happens if you have a number 1 over the square root of 1 minus 1.3 c squared over c squared? What do you get? Anybody? Imaginary numbers, okay. And you know you fucked up, excuse my language. You made a mistake, right? Sorry about that, sorry.
Sean.
I'm sorry. But you know you screwed up. There's no way, you can't do that, okay. You can't do that, all right. So we've got to figure out what the right answer is. And it can't be greater than the speed of light. Okay, so we're not gonna derive it. If you want to derive it, then you go back to the definition of velocity. It's the rate of change of position with respect to your time, okay? And I can do that in, if you want to do it as a supplemental thing in office hours or something, make an arrangement with me and I'll show you how to do that. Otherwise, we're just gonna take the equation. So I have the Wikipedia page pulled up. And where is it? Here it is, okay. And I have the equation all queued up. Okay, so here it is. Okay, so this is the equation right here. Okay, so the speed as measured by a stationary observer is u, right, is equal to v plus u prime divided by 1 plus v u prime over c squared. Okay, so again, we're not trying to figure out where this came from, but just trust that it works. I mean, I guess we could show that it works. I could show in some situation, I could show a nice simple situation. Okay, so everybody wrote down the equation. So u, this is as seen by a stationary observer. Okay, that's u. And then u prime is the speed seen in the moving reference frame, right? So I showed you this before, but oh, so let's do it with this picture here, right? So the Earth would be the stationary frame of reference. The spaceship, the rocket ship, is my moving frame of reference. And this is moving with the speed of 0.8 c. But the letter is going to be u prime, right? What I see in the prime situation is this speed right here. So now, just to show you that it kind of works, what if u prime was 0, right? What would you get then? U would equal v plus 0 over 1 plus v times 0 over c squared. Well, that's gone. You just get v. And that kind of works, right? That means that this is moving as fast as the rocket is moving, which is v. So it's good. But let's see what happens now with my problem that I had here. So 0.8 and 0.5, go ahead and solve the problem. What do you see from the Earth frame of reference? Not quite, Tom. It's what did I use? 0.5 and 0.8. It's not 1.3 over 1.75. You're close, but not quite, right? Got to multiply. So 0.8 times 0.5 is 0.4. So 1.3 over 1.4. Yes, that's correct. Okay. And so the answer is, what do you get? About 0.93 C, something like that. 0.928, something like that. You guys get that? Okay. So we're okay now, right? We have not exceeded the speed of light. We have not violated the concept, the concept that particles cannot move faster than the speed of light. So this is the relativistic velocity addition, right? So it works out, right? It works out that we cannot go faster than the speed of light, even though on initial glance, our first glance, it kind of looks like we might be. It's just not possible. And no matter what you put in here, as long as it's less than c, the answer that you're going to get is going to work out. And yeah, anyway, so that's fine. Okay. So actually, yeah, it's got to be less than c. So everything's good. All right. Well, What else did I want to do today? Actually, I guess that's the thing that I wanted to do. What else? Oh, wavelength. I don't know. Let's see. What did I want to do? I do want to start electricity. We talk about electricity? Maybe not. Not yet. Let's talk about wavelength. Actually, let's talk about wavelength. Let's talk about an electron. Electron, right? And actually, it's kind of an interesting thing when we talk about the electron mass, right? Anybody know the mass of the electron? Pretty tiny, right? That's the charge of the electron. What's the mass of the electron? Okay. So it depends on who you're talking to, by the way.
Like 1.702 times 10 to the minus 31.
Yeah, good. Okay. So I just threw it in Google, right? So it's 9.11 times 10 to the minus 31 kg. Write that down, right? Okay, so that's great. However, if you talk to a particle physicist, that's not what they say. They don't say that, right? And so I'm going to change this in MeV over c squared. I don't know how to put that in, so I'm just going to put this in. Okay, and so it turns out, there it is right here. The mass, according to a particle physicist, is 0.511 MeV over c squared. I don't know if I needed to do it like that. Okay, sorry. I'm just going right here. Didn't work. Okay. .511 MeV over c squared. Okay. So actually, let's just write it down. Here's just what it is. Okay. So this is the way that a particle physicist thinks about it, because in their mind, the rest mass of an electron is the rest energy divided by c squared. So this 0.511 MeV is called the rest energy of an electron, rest energy, and then divided by c squared gives you the rest mass, right? This is the rest mass. So yeah, so this thing has come up again, this EV, and yeah, so maybe I got like 15 minutes. What do I do in 15 minutes? Should we start electricity, electric stuff? What do you think? Who wants to start electric stuff? We talk about what an EV is. Where does it come from? I think we're not quite there yet, but okay. 0.511 MeVs, right? Okay. So what is the M stand? Mega. M equals mega. 10 to the 6th. And an electron volt, right? What is this electron volt? Why is it here? What is it doing? Okay. It's a unit of energy. Okay. So yeah.
I was wondering if we could review kind of what we did today, maybe.
Review what?
Just like where we started today and then how we got here, kind of, and then maybe start electricity next week.
Okay, so well, look at what we talked about. We started with relativity, right? We started talking about relativity.
Yeah, momentum.
And we talked about the fact that some particles have mass and some particles do not. And
right, photons are massless, but they have momentum.
so photons can have momentum. we showed that the kinetic energy formula that Einstein didn't like became something more beautiful when you add mc squared, right? Actually, I'll scan all the stuff that I wrote, so he created this new thing, which led to the formula E equals mc squared, which is, this is one version. This is mc squared. It's kind of a big thing. So I don't know, that's about it. And then we talked a little bit about the fact that
Compton effect.
the Compton effect, right? So that a photon scatters from an electron and it loses some of its energy. So it actually changes color, right? A photon will change frequency and change wavelength because it's giving some of its energy to the electron.
Cool.
And it's also exchanging momentum, right? So it's scattering. That's the word that we talk about.
Yeah.
And then we talked a little bit about the way that telescopes work, this idea of angular resolution. And so if you want a better telescope, you either want to make it bigger or use a smaller wavelength. Both of those will give you better resolution. If you're using a microscope, we said that light works for a while, but then you end up wanting to use, actually, you know what, I think maybe I should do that. Let me not do electric. Let me do that next time. Let's talk a little bit about wavelength, because we've talked about this before with light, right? So what is the wavelength for visible light? Actually, you made me happy. Now I know what we need to do. We need to do this, right? What's the wavelength for visible light, right? Well, it goes from like 400 nanometers to about 700 nanometers, right? Okay, that's the range, from 400 to 700 nanometers. So I said that, you can use an electron, and the electron will end up giving you, a better angular resolution. Why? Because the lambda will be smaller. But I actually didn't show you that. So let's go ahead and try to figure out what speed electron do I want to use so that it has a wavelength less than 400 nanometers? That's my question for you. What speed is the electron that has a lambda equal to 400 nanometers? I'm going to ask this question first. And then if I want it to be smaller than 400, what do I do? Make it go faster or slower?
Faster.
Make it go faster. Lambda will go down, right? So we want to try to use this formula, and here it is, h divided by p. Now I'm going to assume that for the first thing that I'm doing right here, that the momentum doesn't even have to be that fast. I'm going to show you that that works out. And so the formula for momentum I can use is just a nice simple mass times velocity. Okay, I'm just using that. It's fine. This is good as long as the velocity is not too great. And if it go greater than that, then I have to put a gamma in here, right?
Yes.
I'll leave it out for now. Okay, I don't think I need it for now. If it turns out that this speed is significant, like 0.3 c, then I do need this. Does that make sense?
Yeah, I remember.
Okay. All right, so we're going to solve this, right? What speed do I need to get 400 nanometers? Okay. So we want to invert this. Okay, so how do you get V? V equals H over M times lambda. Okay.
Cool, simple algebra.
Okay, that's not hard. Okay, so here we go. Let's put our numbers in. 6.626, 10 to the minus 34, joules times seconds. Okay, that's great. I got that. If I'm using joules, then I have to use kilograms and meters, right? They go together. And so I need what? 9.11 times 10 to the negative 31 kilograms. And then what's the wavelength? 400 nanometers times 10 to the minus 9
Yeah.
meters.
4.00.
Why I did 400 times 10 to the minus 9. It would be 4.00 times 10 to the minus 7. I'm just trying to be
Wait,
lazy.
I thought it's the other way around though.
Okay. 400 times 10, this is nanometer,
Yeah.
10 to the minus 9 meters is 4.00 times 10 to the 7th, negative 7 meters.
All right.
Because you're going to go this way, 1, 2, that's 4 times 10 to the second, times 10 to the minus 9, okay? So 4 times 2, positive 2, negative 9.
Okay, plug that in the calculator.
Okay, so let's do this. Come on, let's do the calculation. What is a number? Somebody got a number for me?
Uh, 1.8 times 10 to the
What is it?
1.8 times 10 to the 5.
I got a different number. Hold on. I got 1.8, but not times 10 to the 5. So this is pretty close to 10 to the minus 30.
My bad. I figured it out.
Oh, okay. Yeah, that's what I got. Okay. So about 18, 20, I don't know, 18, 20 meters per second. Would you agree that that's not anywhere near the speed of light? Does everybody agree?
Yeah.
Okay, so my assumption was correct. I check myself at the end, and it is definitely a lot less than the speed of light. So I'm actually fine. And by the way, that's not very fast. So anyways, that's the speed of the electron. And what happens if you double the speed of the electron? What happens if you double the speed? What happens to the wavelength?
It's smaller.
How much smaller? If you double it, it's 1/2 as big, right? So you can just by doubling the speed, 3,640, the wavelength would become just 200 nanometers, right? That's half the size of violet colored light. It's now ultraviolet colored light. By the way, there are ultraviolet microscopes, by the way. You knew that, right? I don't know if you know that. They're used in manufacturing silicon, actually. They do some, it's not really, anyways, I'm getting off topic. Okay, so that's cool. That actually turned out to be not that fast. But the key thing is that you can actually do a lot better than that too. So the electrons can actually speed up to nearly the speed of light. And when they do, actually, should we try that as our final problem for now? Let's do one problem. Let's do a final problem. What is the lambda for an electron? I have never given this to a student, for students before, not in City College. Moving at 0.9 C, okay? What is the lambda? Now, do we need to use gamma in this case?
Yes.
Absolutely, right? So when you talk about lambda, in this case, it's still going to be H, but now you're going to really think gamma MV, right? M0V, M0V, M. Okay, so we need the gamma. First step, find the gamma. What's the gamma for 0.9 C? You've done this before. Actually, I gave it to you in your homework, I think.
Yeah, it's like,
So what is it?
looks like it is 2.29.
Okay, 2.29, okay, 2.29, okay. So that modifies it. It doesn't make it a huge difference, but it's something, okay. So I have my H, okay, 6.626. 10 to the minus 34. I didn't actually show you guys all the units canceling. Do you want to see that? I don't know. We'll talk about that in a minute. 2.29, 9.11 times 10 to the minus 31, 0.9, 3.00 times 10 to the 8th. Okay, meters per second, running out of space. Okay, so you got a big mess here. I gotta just calculate. 6.626. Okay, got a number? Anybody? Okay, I got a number 1.18. Thank you. Times 10 to the minus 12 meters. Okay, 10 to the minus 12. Anybody would know what that is? 10 to the minus 12. It's a picometer. 1.18 picometers. P stands for pico. Picometer. Okay. So that's pretty tiny compared to nanometer, right? It's a very, very tiny wavelength, and it turns out I can go even faster than this. So basically, these become much more capable of seeing high resolution than a regular light microscope will be. So if you've never looked at electron microscope pictures, it's pretty cool. Electron microscope images. I don't know. I'm sure I can find something taken with electron microscope. Yeah, this is kind of. I mean, there's all kinds of crazy things. Oh, that's pretty cool. That is actually really neat. This is an electron microscope picture of a microscopic gingerbread house, smaller than a human hair. Okay, this is a tiny little piece of silicon, is 10 microns wide. Isn't that cute? Gosh, that is amazing.
Is that real? What?
Huh?
Someone actually did that? They did that as art?
Just to show you that they could. Oh, yeah. And by the way, so that's pretty cool. But actually, since we're on the topic, you might want to know who did this first. IBM logo with atoms. This is an actual picture that was created when I was just starting graduate school. And each one of these points is an individual atom. And so they're pretty big atoms, but anyways, atoms nonetheless. And this is a different kind of telescope / device called a scanning atomic force microscope, or scanning tunneling microscope. Actually, it's scanning tunneling microscope. Sorry, this is that. I'm thinking of something else. So later they did even more. But anyways, you can actually you can see individual atoms now. Okay. So when I was in school, my teacher said you can't see individual atoms. Yeah. How does one prevent vaporizing the sample with the light speed of light? Even though they're traveling near the speed of light, I bet they were Canadian. They don't carry a lot of energy, it turns out, and so even though they're traveling so fast, they're really pretty insignificant masses. So luckily, even at that speed, their energy is relatively, I mean, it's pretty small. So it's able to scatter without destroying the sample. So, All right, well, I think I am going to stop, but actually this gives me a clear direction for next time. Next class, we want to talk a little bit more about electricity, right? Electric fields, right? Electric fields and the electromagnetic force. The electric.
So I did the math, and it looks like this would be X-ray radiation, or somewhere in between gamma and X-ray radiation.
Okay, equivalent to X-ray radiation. Okay, great. And so, by the way, we're not even at the limit at all. We can go much faster than this. And as we do, the faster we go, you see now gamma is going to enhance this, and you're going to get something which is much smaller than.
So at CERN, do they accelerate the particles very close to the speed of light, right?
They can go very close to the speed of light. They can definitely be relativistic. So it turns out that actually, well, that's one of the questions I'm going to be asking you. How hard is it to make an electron go relativistic speeds? And I don't want to give it away, but it turns out you can do this at home. You can make electrons go relativistic speeds. Okay, so I mean, I'll show you next time. We'll do the math, right? And I'll prove it to you that you can do that, right? So actually, it's too bad we can't be here together, but maybe I can still do a demo. There's actually something really fun that we could do. Okay, so I am done with lecturing and talking about this stuff. Did I see? Oh, the floor mat? No, I didn't see that. Let's take a look again. Where is that again? IBM. Oh, I jumped. The floor mat. Oh, that is hilarious. Oh yeah, they're totally Canadian, McMaster. Okay, so Tom actually noticed something, a little detail. If you look very carefully, there's a Canadian flag for the doormat. And this is McMaster University, which is a Canadian university. Very good. So yeah, that's actually, so here, Canadian Center for Electron Microscopy. That is hilarious. Oh my gosh, the windows and everything. So fun, that's cute. And that is the width of a human hair. Right. Oh no, 1/10 of the diameter of a human hair. Okay, it's tiny. So yeah, anyways. So I need to give you guys some problems, but I don't have them yet. So what I'm gonna do is this afternoon, I will create some problems and I'll post them for you. And they'll have something to do with relativity. And so we covered a number of topics concerning relativity. It had relativistic momentum, energy. We had the addition of velocities. Those are some concepts that we covered today and are already on your equation sheet. I don't think we did anything completely new. I think I did show, I don't know that I did everything that's on the equation sheet. I think I might have added a couple of things that I haven't done before. But anyways, they'll be related to this topics that we talk about, and you have a week to do them. And yeah, that's it. Any questions? You guys have any questions?
No questions.
Oh, how about, I didn't show you this, but do you guys know what a joule is?
Yeah.
Is the accretion disk relativistic for?
Kilograms.
I'm sure it is. The question says, is the accretion disk relativistic before crossing the event horizon? I'm actually sure it is. Okay. A joule is a kilogram times a meter per second squared. So if you take a joule times a second divided by a kilogram times a meter per second, right? You're going to get a kilogram meter per second divided by, what did I do wrong? I did something wrong. Kilogram. Oh, I messed up. Sorry, it's not a kilogram meters per second. That's a Newton, sorry.
Yeah,
Times a
so
meter, there we go. Times a meter divided by kilogram meter per second. And you end up with meters. Okay, so it ends up with meters. All right. Yes, okay. All right, any other questions? You guys are easy. Okay, well, thank you guys very much for attending. And I will post some questions for you. Does it emit synchrotron radiation? Charged particles emit synchrotron radiation. Yes, no, they don't even have to be moving at the speed of light. Johnny, did you have your hand up? I'm sorry, I just saw it. I didn't pay attention. Or is that from before? I think it was from before, maybe.
Thanks, Sean.
Okay, you got it, guys. Thank you. Yeah, no problem, man. That's fine. All right, we'll see you guys next week, and I'll post some questions for you. I'm hoping it'll be later today. If not, it'll be tomorrow morning. Okay, and I'll have some nice problems for you to work on. All right, thank you, guys. So have a great day. Have a good
See you, Sean.
weekend. Bye.